So what we are going to do today is, and let me tell you, I like this class a lot. I like teaching this class because I feel like we kind of gradually move through things. If you remember last time, what we were talking about was physical properties and chemical properties. And so we use terms like if something burns, that's a good indication that something underwent or that's a description of a chemical change. So it's almost like when you talk about a physical property or a chemical property, you start to talk about it as a physical or chemical change. So like, um, let me ask you this. If you have ice water, or if you have an ice cube, and then you have a puddle of water, chemically, are they the same? Like, what is water, chemical wise? Yes, they're absolutely the same because whether it's frozen or liquid, still H2O. Now, so that would be an example of a physical change. A chemical change, well, that can be a little bit trickier. We talked about milk spoiling or curdling. Well, that's an example of a chemical change because what's happened is the chemicals within that milk have undergone changes. Like the proteins have changed shape and they've changed structure. Now, to capture this, we've got this really great meme picture of, does anyone know who that is? Because if the answer is no, nobody knows who that is, well, then I'm going to have to change my slide. If you can, David Bowie, perfect. Okay, good. I figured, I mean, he was a musician far before I was born, so I figured he's a little bit more timeless. Okay, so David Bowie, changes, physical changes. Some examples. We just highlighted one. An ice cube melting. No bonds are made or broken. That is this right here. I'm going to switch to the highlighter. Yep, I've got the highlighter. This is a hallmark definition of a physical change where no bonds are made or broken. Now, that is the case when an ice cube melts. The shape has changed, but it's still water. Next up is if you have a mixture, separating components of a mixture. So if you had like, let's say you went down to the Gulf and you picked up a solution of the Gulf water, so the beach water. If you picked it up and you put it in a glass, you'd be able to separate some parts of it. So you'd have sand that you'd be able to separate out. Well, that sand, in order to separate those components, to separate the sand from the water, well, the sand is sand. You're not breaking any bonds between the sand and the water or anything like that. Another physical change would be making a solution. So if you make Kool-Aid, for example, that Kool-Aid, that crystal Kool-Aid, that's going to go into solution. That's going to dissolve and you're going to make that solution, but there are no bonds that are being broken. So a word here, dissolve, typically indicates that no bonds are broken. Now, I would say that these two right here are your toughest ideas for a physical change because I don't know, there's part of me that thinks about something dissolving and I just think, oh, well, a bond has to be broken because that there was a solid that was there and now it's not a solid. But I assure you that when you make a solution, you're exhibiting or you're displaying or you're seeing a physical change, a physical deformation. And I think that this is kind of like the first one, an ice cube melting, a physical deformation. These are a little bit easier to wrap your mind around. And these are just, this is one of the kind of extents, the links that I'll go to, the sacrifices that I'll make. I've got a perfectly good piece of paper here. Look at that. Dramatically, I just ripped it in half. But you know what? Still pieces of paper, still two separate pieces of paper. This is an example of a physical change. Okay. In addition to that, if it's dented or if something's stretched, it's still going to be a physical change. Now, these two, where you have separating components of a mixture, this one I always like to bring up, in part because in Texas, what is a major industry in the state of Texas? And I'm thinking specifically, oh, I don't even have to go any further. Oil and gas industry. If you're from like Sugarland or Pearland or anywhere in the one of those Houston suburbs, you drive past, or if you drive down to the coast, you're going to see refineries, and you see these really tall towers. And those towers, what you do with those towers is you get crude oil. And with that crude oil, you put it in here, and then you put I'm going to do a flame here. That's a flame. The sound effect made it a flame. So you take that crude oil and you heat it up. And when you heat it, that crude oil, if you can imagine that it's like a really thick slurry, well, what's going to happen is that crude oil is going to separate. That crude oil is a mixture of octane, kerosene, then jet fuel. And as you heat it, these different components in this crude oil, this really kind of sludgy mixture, will separate. And you'll be able to capture these different solutions. So you'll be able to capture kerosene here. And you'll be able to capture octane here. Because you're heating up this mixture, and these different gases, or these different gases are going to evaporate. But then you're going to be able to capture them because they're going to undergo what's called a phase change, another physical change. They're going to separate based on their boiling point, a physical property. I like to highlight this because I think that there's quite often, I know that people who have any association with science, like what you guys have in this class, there's this kind of intimidation factor. Like, oh, if I wanted to invent, whatever piece of technology, I have to think of the smartest thing that anyone's ever done. That's how it is. I have to understand this the way that nobody's ever understood this. Well, let me ask you this. Is there lots of money and wealth in the oil and gas industry? Yes, yes, yes. There absolutely is. And what are like this process of refining and separating jet fuel, kerosene, octane from a crude oil mixture, is there money in that? Absolutely. And what is the extremely complex technology involved with that? And I'm not trying to I'm not trying to simplify it, because it's certainly not technically simple, but that entire process is dependent on and based on a physical property. So anytime you think like, oh, well, I have to think of the most clever thing that anyone's ever thought of. No, you don't. You have to understand physical properties, chemical properties. If there was another technique, like if there was a technique where you could separate the chemicals or separate these components that did not require, massive plants and massive towers that were 200 feet in the air, do you think that that would potentially be, and if it was cheaper, would people use that? 100%. Absolutely. That's how we would separate these different components. But this is a technique that basically you heat things up and then they condense. They evaporate and then they condense and then they're captured. So that's using physical properties and physical changes to separate components of a mixture. And oh no. Okay, good. I am recording. Sorry. Um, and to basically make a lot of money in some senses, but also to get a lot of energy out. Okay, so next up, chemical changes. So in a chemical change, bonds are going to be broken and or formed between molecules or atoms. So observations that indicate these. Temperature changes. Is there anyone in here who goes hunting? And in particular, I'll say goes hunting or, I mean, any outdoor activity in the dead of winter in, I'll say West Texas or Colorado or any other state where it gets very cold. Okay. Now, if you've gone out to deer blind in Brownwood, my sister-in-law went to school there, I think, in the dead of winter, in like the early weeks of February, and you've been in a deer blind, it's going to be chilly. But sometimes what you do is you get these, you go over to Academy or yeah, go to Academy and you get those little packets, those warming packets that you basically just crack down. And what happens to them? Oh yeah, I said warming packets. They make your hands warmer. That's a chemical reaction that's taking place in there. So a good indicator of that, what? Propane heater in a deer blind? Well, thank you very much for that, Aiden, because that is also an example of a chemical change. Because you're burning propane, and what are you producing? CO2 and H2O. So perfect. Thank you. That works as well. So a temperature change is a good indication that a chemical reaction has taken place or a chemical change is taking place. When heat is given off. Another example would be light would be produced. A color change. Think back to, again, you make that milk and you let it, or not make that milk, but instead you get a glass of milk and you let it sit out for 3 days. It's going to stink. It's going to grow a really nasty biofilm. And then somebody's going to come along and be like, what is that? What? Why did somebody get warm cottage cheese out? Oh, nobody got warm cottage cheese out. They got milk out. And it naturally turned into cottage cheese. And it's going to smell. And it's going to have a color. Maybe even some bubbles are going to form. That's probably after like 5 to 7 days. It's at that point, you've seen it and you forgot to do something about it. And the you in this case is this guy right here. Because I did that. I remember that. My brother and I left a glass of milk out and yeah, we forgot to do something and then again forgot to do something about it. It was really disgusting. And I mean, heck, you wouldn't want to taste the congealed and curdled milk, but based on the smell, you can imagine what the taste is. Now, with that said, has anyone ever made guacamole and let it sit, or not let it sit, but day one, ooh, it's good. Day two, it's still good. It's got a little bit of brown stuff on top, but that's like oxidation. You clear that off and it's gone. If you let it sit for a couple more days, what happens to it? And sit in the refrigerator. Can anyone describe the taste? Yes, it gets brown. It gets sour. That's absolutely right. And when it gets sour, that's a presence of acids. So acids make that taste not so good. So you're kind of done with it at that point. Okay. How's everyone feel about chemical changes, physical changes, chemical properties, physical properties? Can I get thumbs up in the chat for I'm good? And then a thumbs down for I'm going to go take a look at it maybe over the weekend. Okay, we got some thumbs up. Good, good, good. Okay, cool. I think it's helpful to try to think of some changes that you've seen and think like, is that an example of physical or chemical change? And you're welcome to email me if you want, or just try to think about like, are any of these things right here taking place? Or is it something like this? A seal? Is that a sea otter? I'll take that as a thumbs up. And I'll just go with that's an emoji in a different font. Okay, so next up is the classification of matter. Now, I would say that the classification of matter is probably something that you've talked about in any other science class that you've ever taken. And when it comes to the classification of matter, we really talk about three different major states: solids, liquids, and gases. Now, when it comes to solids, liquids, and gases, I think that this visual right here captures what's taking place. Imagine that the solids, liquids, and gases are made up of individual atoms. In a solid, these atoms are organized. They're basically stuck in the same locations and they're not going to move. So organized, no moving. Whereas in a liquid, less organized and more movement. In a gas, I would go as far as to say no organization and even more movement. Now, these states, these are all examples of physical states. Or these, yeah, these are all examples of physical properties. So whenever I talked about separating crude oil, you're separating things like you take that liquid, crude oil, and you separate it into different gases, and then you capture those gases at different elevations in those chambers or in those towers, those distillation towers. Now, important states of matter characteristics. Solids have a defined shape. Liquids do not have a defined shape. That seems a little bit weird because, well, whenever I pour my coffee into this coffee mug, does the coffee in that mug have some restrictions to it? Or does it just flow wherever it wants? Now that's kind of that's not the best wording, but it does have some restrictions because the sides of my coffee mug restrict where that coffee can be. Absolutely right. The coffee has restrictions that are imposed by the container. So a liquid is going to be limited by the amount of it and by the shape of the container. Now, if we compare that to a gas, and whenever I apologize if you don't like stories. I don't really know what to tell you if you don't like stories, because I think that stories are like essential to human existence. But when I was in sixth grade, there was a girl on one of the other teams, because we were divided into teams, and she went into the bathroom and she broke a stink bomb. And that stink bomb, I don't know, has anyone ever seen a stink bomb? They're like in little glass vials, and you just snap them, and then the liquid that's in those glass vials, it quickly converts to a gas, and then that gas fills whatever room it's in. Now, if we were in a classroom together and I broke that, and I had a stink bomb and I broke one of those, that gas would fill the classroom and it would stink. Okay. Now, when I was in sixth grade and this happened, this girl broke this container and it filled the bathroom. And then it went beyond the bathroom because it got into the ductwork of the school. And then it filled all of the rooms of the school because it got into the ductwork. And that day, we all recognized her as a hero because it was at 10 a.m. and everyone got out of school early. It was wonderful. They brought the buses, and it was like the best kept secret for about 3 days. Like it was the best, worst kept secret. Every kid knew. It was like, oh, it was so and so. Yeah, yeah, shh, shh, shh. But then there was one kid who was like, well, I need to let Mr. Wolf know who this was. And everyone was like, dude, you don't. You don't. You got out of school early too, man. Be cool. And he wasn't. At any rate, that's what a gas does. A gas has no defined shape. The only definition of its shape is the container that it's in. The container that, the progression. I always like to think about a progression. That gas was originally contained to that small glass vial. That vial was broken. What's the new container? The bathroom. The bathroom and the ductwork. The ductwork and then the entire school. And so then ultimately what happened is they propped all the doors open. And of course it was a school, so they didn't have any windows to open. So they propped the doors open. And now what was the new container? The entire city, the entire atmosphere, the entire globe. And, slowly but surely the odor dissipated. Now, so liquids are different from gases. They both have an indefinite shape. They're restricted by the shape of their container. Now, solids have a defined volume. Liquids also have a defined volume, which this defined volume will limit the shape of a liquid. Because if I fill this coffee mug halfway up, well, then it's not going to spontaneously get to the brim. It's going to stop about halfway here. Whereas a gas, if I were to get like a CO2 canister and spray some gas into here, what's going to happen? Well, it's going to fill the container. It's going to fill the room. It's going to occupy every part. So it has an indefinite volume. So these are the biggest differences between solids, liquids, and gases. Shape and volume are big differences between solids, liquids, and gases. Now, all matter is going to be either broken into a substance or a mixture. Now, substances are either pure elements or they're going to be compounds. Mixtures are classified as either homogeneous or heterogeneous. So a homogeneous mixture is going to look the exact same throughout. A heterogeneous mixture is going to have some variability. I always think about this like marble or granite. Now we have lots of beautiful places on campus where you can see, a granite sculpture or a granite bench. That would be an example of a heterogeneous mixture because if you take, here's the entire bench. If you look at this subsection right here, you're going to see a pattern to it. And then if you look at this, it's going to be a different pattern. It's going to look somewhat similar, but as you inspect a little bit closer and closer, you're going to be like, there's some differences there. Now, your takeaway from this slide should be homogeneous versus heterogeneous. An example of a homogeneous mixture would be something like brass or steel. Those materials, you're not going to notice one distinct thing within there. Okay, now if we jump back when we talk about substances, an element or a compound. An element is composed of one type of atom. An example there would be Au, gold. An example of an element would be, well, again, we've got one type of atom. This is 2 oxygen atoms. So That's two of the exact same type of atom. So O2 is an element. This is kind of confusing because I know that whenever I hear element, I think of single. So a singular element. Well, yeah, that's true. This is two of, O2 is two of one singular element. A compound. I always hear that word and I think CO. So I think of like complement. I think of conversation. I think of multiple things coming together. Well, a compound is composed of two or more elements. An example of that would be water. H2O is a compound. Table salt, NaCl, is a compound. Now, here we have an atom versus a molecule. Well, our smallest characteristic part of an element is an atom. A molecule is composed of two or more atoms. So think about all of this as like when we're describing something. Okay, I'll take this cup right here as an example. Looking at this cup, how would we describe it? This is matter. Now, this cup right here is a mixture. Now, if we look at this cup, I see that it's blue, and then I see there's this marking pattern on here for Big Shots Golf in Bryan, Texas. I'd see that and I'd say, okay, well, this part of it is different from this part. So this cup right here with this logo on here I see some differences. So would I classify that and add this to the chat? Would you say that it's a homogeneous mixture or heterogeneous mixture? And I'm talking about my visual of the entire cup right here. Yep. Yep. I'd classify this as a heterogeneous mixture because I'm talking about the whole thing. Now, if I were to cut a portion of this cup, and let's say that I only had this part where I look at it and I see, oh, it's nothing but, absolutely. So I'm going to apply the definitions to this example. So if I were to cut a portion of this cup and look at that cup, and I saw that it was uniform, if it was completely uniform, then I would say, okay, well, this uniform cup is homogeneous. Now, when I look at this entire cup, where I have a blue portion and a white portion, well, I'd say that those are differences. So this is a heterogeneous cup. Now, I'd just like everyone to, whenever we're adding to the chat, let's keep it on above board and let's talk about things that are relevant to this. So homogeneous would be a small subsection of this. Heterogeneous is where I'm looking at the entire cup. And I see that, okay, well, that's white, this is blue, those are differences, but it's a part of one complete thing. So that would be a heterogeneous mixture. Okay. So now when we talk about atoms and molecules, a molecule is composed of two or more atoms. H2O. Well, H2O is a compound and it's a molecule. This is where it gets a little bit tricky because H2O is also, I'm going to say, and a compound. O2 is a molecule, but it's not a compound. It is also a element. Okay. So these definitions, these tend to, like, people get mixed up on these because an atom of gold, AU, well, that's also an element. Ask yourself, what is there? Is it one of the same thing? Or sorry, is it two of the same thing? Then it's an element. If it's two or more atoms, well, then it is going to be a molecule. Okay, well, we're gonna end a little bit early today because that's what I've got for y'all. We'll dig deeper into this stuff next week. This wraps up what we're going to cover from chapter 1. So if you wanted to look back and kind of put together like your own sort of study guide almost, the slides from today and previous slides, that would be a good place to go. I'm going to end my recording.